So we will begin the session. So good evening. So welcome to the session on exploring nonlinear dynamics from basics to applications. So this is the last session. So till the 12th session we have seen different nonlinear dynamics basics, and we have talked about applications in engineering, physics and aerospace. So we have talked all this in the previous lectures. So this session I would like to talk on the system where if you are not having a dynamical system equation with you. So all the time you may not be able to get a dynamical equation for your systems. So in that is the case, how we will be dealing with. So we will conclude this session with how you can work with these kind of systems also. And so in the lecture series, so this is the approach, and we will be talking about data driven approaches. And so these are some of the books and references. So this time you can refer the CMA review papers, where I have taken some details about the data driven approaches, and this time you can refer to the Steve Brunton and his videos to understand more on Koopman operator. And so we will begin with our session 13. So till now we have seen that if you have a dynamical system of this form, x dot is equal to f of x, and where f is a function or a vector field that tells you how the system changes at a given state and time, whereas the x here, it represents the state of your system. The state of a system, we mean that it's having the minimum set of variables which requires to describe the evolution of the system in time. So that's what this state variable x was. Now when you do have a system of a dynamical system equation, we saw how to find the different fixed points, how to tell whether your trajectory is moving towards a particular point or not, and how to get to the different bifurcations and analyze them. So these are the things which we have seen in the previous sessions. Now when we do have when we have a dynamical system equation, we try to think in this kind of bifurcation analysis, bifurcation theory and all we try to look into. However, interestingly, not every systems that we know, they don't have access to these kind of equations. Maybe you have a partially known or completely unknown you may be about the system. For example, you have this climate system where it's so complex that you can't write properly the dynamical equations, or you have the brain system where you don't have much access to these equations, which are either partially known or you have completely known on this. And other areas like disease spreading and all these regions, you don't have a dynamical equation to express your dynamics. So discovering equations from data is very important, because nowadays we have so much of data from experiments and other simulation results that we need to discover certain equations from this using this data. It's very important, and which is something what Koopman has came up with. So we will discuss on that. So so till now what we know is like, if you think back, we can say that we know properly how to explain a linear system. And in the linear system also, if we have a constant coefficients, then we can find the eigenvalues and eigenvectors of this system, and we can find how the system eigenvalues evolve, and we can get the solutions for this system. And in this kind of linear systems also, we are very capable of solving the constant coefficient linear systems, whereas if you are having a variable constant coefficients, then it's more complicated and we need to do more things on that. But now in these kind of linear systems, whatever we have learned in the dynamical system theories and all, these are very dynamical system equations, they are very restricted to very small perturbations. If you are having a non-linearity or a epsilon greater, very higher perturbations in the system, then it's still not properly understood how to analyze these kind of things when you are having in a dynamical perspective also. So we want to use the data which you are getting from, so your real experiments you can do, you can get data from brain and you can get data from the climate's variation and all. So we should use this data to predict the future states, and with that we want to understand the state of the system. So that's what by data driven approaches we try to think of. And one of the, so complex system is behaved as, thought of as a complex systems are full of interdependencies. They have multiple subsystems and they have a lot of interdependencies among each other, and they are hard to detect, and the nonlinear responses are also very much important in these systems. And so we will just speak about the how this Koopman was evolving and what was the era where people were thinking of this. So during the time when the Poincaré and Lorentz were discovering their important systems in the Lorentz equation, in the butterfly effect or three-dimensional problem, where Poincaré was able to show with the geometry and all. During this time, people were mostly focusing on the dynamical equations. They had x dot is equal to f of x. So how to solve those problems? So this was the time during the Poincaré and Lorentz. During this time, the system like the geometry of fixed points, periodic orbits, stable and unstable manifolds, these were all pretty famous at those times. But then actually in a pendulum the equations are very simple, but the dynamics you are seeing is very complicated, and you will see it if you are taking a double pendulum instead of a single pendulum. You will be seeing very more variety of dynamics the system exhibits. Now to understand those, during this time in the 1930s and all, Koopman showed a way, and in his paper in 1931 in the Proceedings of National Academy of Sciences, he says that if you think about the Hilbert space, or for currently we don't need to go into that, he says that if you are thinking about the Hilbert space of all possible measurements, you could take off that system. So this, you are shifting your current dimension of the system. So you are in certain coordinates. Now you are changing the basis to a higher infinite dimensional space of measurements, such that in that space you can do linearize, you can apply this linear theory which you have learnt in the your basic linear algebras and all. So he wanted to use the data which you have, take this the high dimensional data and project it onto an infinite dimensional space where you can express your position, that is you are moving from one state to the another state in a you can correlate a linear relationship between 2 points. So we will see what he means by that. So this was his theory which he proposed. And so what Koopman's innovation was, he was to propose a mathematical framework that could simplify the analysis of these complex systems where you are having very high dimensional data and all. So he introduced the idea of using observables. So we will talk of how to choose an observable and all in the coming slides. So he introduced the idea of observables. Observable is nothing but which are the functions of the system state variables which represent the behavior of the system. So those parameters is what we term as observables, and by applying a linear operator to these observables, he aimed to capture the system's evolution over time in a more manageable way. So that was his contribution during this. So we should remember that this was the time where Poincaré and Lorentz were pretty famous, where they were trying to solve all the dynamical equations and all, they were trying to do that. Now, so in Koopman theory, it defines that, so you have a equation of the form dx by dt is equal to, this is nothing but x dot is equal to f of x, say t and nu, some variable is there. Now if you are able to define certain variable, some other variable called y, which is say a function of g of x. Now if you are able to write into certain this kind of form, then Koopman says that the gth of xk plus 1, so the next point in this higher dimensional, infinite dimensional space, is nothing but a operator times the previous time step, that is g of xk. So finding this Koopman operator, and so eventually what it tells is you have an equation of the form dy by dt is equal to k times y. So this is the simple, in short, in brief, if you say what Koopman has defined. You had a high dimensional case here, dx by dt equal to f of x tu. If you are able to write a function of the form y is equal to g of x, such that in that form each step, next step, is equivalent to sum of some operator times the previous step. So this is, now it has become like a linear system, and you can observe here y dot is equal to ky is a linearized system over here. So what was the main black point or bad drawback here was Koopman never mentioned how to find this g. How to find this g, he was not able to explain. But that was the challenge that was there on the upcoming generations, to see how this g can be found out and how to do all this. Then so now we have reached to a point where you have an idea that if you are having a high dimensional system, and if you are able to say, now I will say it's like some magic you use, and you have certain parameter and you make it into certain higher dimensional system, there you can apply all your linearization theory and all you can apply there and get the information which you can't get from the actual high dimensional data. So that is a idea that Koopman was having. So that's the main idea of using a Koopman operator, and for all this you need high dimensional very high quality data, and high dimensional data is required. And in the current, with this generation of computer generating very huge amounts of simulation data and experiments being carried out very rigorously, there are tons of data being available now in the current world. So this kind of approach, it seems to be very feasible, you can say, and it seems to be giving you an approximate values of the solution, which are useful in an engineering perspective or in a real world systems. You need nearby answers to tell your system state and all. So this approach was very useful, and people were working rigorously on these things. Yeah, so before going to Koopman understanding and all, we will try to see one example, small example. So we will take a simple nonlinear dynamical equation of the form x1 dot equal to nu x1, and the other equation x2 dot is equal to lambda times x2 minus x1 square. So this is a simple two coupled equation which we have. Now I will just shift to my tab over here. So we will take a small example. Say you had x1 dot is equal to nu x1 and x2 dot is equal to lambda times x2 minus x1 square. So now you had this equation, and if you try to use our dynamical system method and all, say for that I will write, say, a function y1 is equal to x1. This is how you try to reduce your second order equation to first order and all. This was the small trick which we are using. So we will consider that here first. So if you take some y1 which is equal to x1, then this implies y1 dot is nothing but x1 dot, which is nothing but x1 dot is nothing but, from this equation 1 you can say it is nothing but nu times x1. This is eventually nu times y1. So you have written the first equation into the form of the second variable, that is y1 terms you have written. Now we take another variable, say y2, which is equal to x2. So now we are trying to convert that. Then y2 dot is nothing but x2 dot, which is equal to lambda times x2 minus x1 square. From second equation you can see that this is nothing but lambda times x2 we wrote, that is y2 minus x1 square. So you can write x1 square is now a new variable because we wrote y1 is equal to x1. So we can't write y1 square is equal to x1 square, we can't, because y1 is a in another dimension, it is given to only particular x1 value. So we need to take another variable for this x1 square. So we take y3 as x1 square. So then it implies whatever you have y2 dot is nothing but lambda times y2 minus y3. So this is now your fourth equation which you have. So now since you had an additional term called y3 here, so if you take y3 dot, it is nothing but 2 times x1 into x1 dot. So this is nothing but 2 times x1, and x1 dot you know from the equation 3 is nothing but new y1, or you can directly write it as new instead of x1. This x1 dot can be written as new times x1. From the equation 1 itself you can directly write. So this becomes 2 times new x1 square. This is nothing but 2 times new into x1 square is what we have written as y3. So this is your fifth equation what you have. So from the Koopman linear system approach, so which means that you need to convert this into a form of dy by dt is equal to some Koopman times yy. Okay, y you need to do. So if you try to make this all equations into this form, so how we will write is, we will have d by dt of y is nothing but, now you have three different terms for it, that is y1 dot, y2 dot, y3 dot. This is equal to, sorry, now since you are putting derivative outside, you don't need dot here. y1, y2, y3 is equal to, so we came up to the, so okay, I will, for better understanding, I will write the equations here. So y1 is nothing but x1, y2 is nothing but x2, and y3 is nothing but x1 square. So when you are take, this was what we have taken, and if you take the derivative of them, so y1 dot we got it was mu times y1, and y2 dot we came to was lambda times y2 minus y3, and y3 dot is nothing but 2 nu times y3. So these are the final three equations which we came. So now we have, if you observe, we have converted all the x1 x2 terms into the other variable y1. So if you are able to do something like this, so I will write it down for clarity. So if you are able to convert that equations into this kind of set of equations, then you can write like this, d by dt of y1, y2, y3 is equal to, now the coefficient of y1 is new, so you will have new over here, coefficient of y2 and y3s are 0, whereas for y2 dot you have coefficient of y1 0, for y2 you have lambda, and for y3 you have minus lambda. Similarly at y3 you have this 0, y2 coefficient is 0, so you have only 2 nu, and finally you can write it into the matrix form y1, y2, y3. So this is the form which we have. So here if you see y1, y2, y3 is nothing but x1, x2, x1 square. So this is the thing which we have used. So now you have converted your set of equations into a Koopman linear system where you had a operator. So if you take this operator as k, then you can change from one dimensional to the other. From y1 dot you can find the y. So it's like a linear operator now. It is of the form dy by dt equal to some k times y. So this is the approach which we are trying to see. If any of this system of equations which you have, can you use these kind of methods to come to the other state or other space which we say. And so I will just shift here. Yeah. So said that we saw these steps written, then now say when we did this analysis, we saw that our dynamical equation initially could have had n fixed points. So that is dx by dt is equal to some function of x, t and u. It could have n fixed points from the dynamical system equation. But when you are converting it into a linear system, so dy by dt is equal to k times y, you are converting it into it. Now it is a linear system. So for that linear system, you will have only one fixed point. So now the question arises, where are the remaining fixed points when you are converting your actual equation to this Koopman operator linear system, where all other fixed points are vanishing. So the actual thing is, we are actually building the Koopman operator around one of the fixed points, and the remaining fixed points, it moves to infinity. So our Koopman operator is focusing on the most around one of the fixed points which is most dominant in the system, and we are trying to do all the things near to that. The remaining fixed points, they move towards infinity. So we will see how to do that when we are converting from a given equation to another. So before that, now every time we can't perform this kind of conversion. We are getting a equation like this directly, y1 equal to x1 term. If we try to do on a simple problem which I have shown here, d by dt of x is equal to x square, if you take that simple equation, and if you try to implement the same approach which we did a few minutes back, we will see what happens in that such condition. So I will just share this tab screen. We take a simple example of d by dt of x is equal to x square. So if we are now considering this simple equation, and we do the same approach, like we take y1 is equal to x and y2 we take as x square. If you take, now if you do this process, so we will have y1 dot is equal to x1 dot, which is nothing but x square over here, and if you take y2 dot, this is nothing but d by dt of y2. From this equation, it is nothing but 2x x dot, this is nothing but 2 times x. Now x dot is nothing but x square. So if you do that, you are coming to x cube. So y2 dot is equal to 2x cube. So now, as I told, x cube is a new term, so you need to give x cube as a new variable, y3. So now y3 is equal to x cube you got. So say this is your first equation, this is your second equation. Now you had a equation y3 is equal to x cube. So in order to, now you need to find y3 dot. So if you do the y3 dot now, this is nothing but 3 times x square into x dot. So now this goes to 3x square into x dot will be now x square. So this will now go to 3 to the power 4. So now this becomes your fourth equation. Now if you observe, if you are keeping on going, now x4 is a new variable. So now you need to give x4 is equal to as y4. So this is your new a value that you need to give in the Koopman linear space. So if you keep on going like this, you will see that finally you will end up into a form like d by dt of y1 y2, it keeps on going up to yn. This is nothing but, and now if you take the coefficients over here, so initial x has 0, x square value will be 1, and remaining things will be 0. In the second case, when y2 you are considering, equation 2, you have the x cube term has the coefficient, so this will be 0. Here you will have 2, then remaining goes on. Similarly for y3, you had at x4 you have the coefficient. So now this keeps on increasing in this and this direction. So this is the matrix you have, and here you have the other things. So now if you observe, this is keep on increasing. You are not even terminating to any particular value when you are increasing in such a manner. So if you are if you expect that such simple substitution can be made and you can convert it to one space to another space, here we come up to a problem called the closure problem, because as you can see here, the system keeps on going down and down. So you need to keep on adding more and more number of points into the system, more and more values into the system, more and more variables y1, y2, y3. You need to be keep on adding them, and it never ends. So this closure problems comes into action if you are trying to convert this dynamical equation into this linearized Koopman operator theory. So what we try to do here is, so this we saw, and we saw that it keeps on increasing and never goes down. So now we have pretty long equations like dx by dt equal to f of, you have a lot of equations that is of this form, like example the Schrodinger's equation, the Maxwell equation. In fluid dynamics you have the Navier-Stokes equations. Now for a new system which we don't know, the function f is now completely unknown. So finding the y of k in terms of g of xk and making it into the form of dy by dt is equal to ay is challenging, and the question arises why we want this solution, an approximate solution in another space. Why you want to do all this? So it's like this Koopman operator theory can predict the future for a very it's for a smaller scale. It can predict the values with the current system equations. So if you have certain values, and with this operating methodology, you can predict the future points, where it will be lying out to. It's a short-term prediction method, not a long-term prediction method, what we say Koopman operator. So it can predict the future values in the system using the present dynamics. If you are giving the current dynamical system equations, not dynamical, current data, with your current data, if you are able to make certain form into this form, ay form, and you can predict the nearby future for a very shorter period. That's the limitation that Koopman has. Now from the Koopman operator framework, we have certain steps to be carried out when we are trying to perform these actions. So the first step involves observable selection. So we need to choose the observables that captures the state of the system. So as I mentioned, the state, the set of variables where your system dynamics which can show the dynamics. Then once your observables are selected, we need to do something called as dynamic mode decomposition, where it's a powerful data driven analysis technique which is used to extract the underlying dynamical patterns or coherent structures from the time series data. So that's what dynamic mode we say by. So the dynamic modes present in the system, which for a fluid mechanics or any of the system, you can consider them as dynamic patterns or coherent structures. So these structures are the dominant structures it tries to capture from the time series data, and DMD or the dynamic mode decomposition can particularly valuable in cases where you have observed data but you have a lack of understanding of the mathematical model of the underlying dynamical system. So we try to use these methods to make the Koopman operator framework. So in basic steps, so what we try to do in a Koopman operator, to compute a Koopman operator, what are the basic steps we try to follow is, the first step is you have a time series, say you have capital X, which is a time series of x1, x2, x3, and it keeps on going up to xm minus 1. And so we call this as one snapshot of the system, and we try to take the next snapshot. So if you are, say your time series started from x1 and it moved up to xm minus 1. Now you are taking the next snapshot x prime, which is starts from x2 and it moves up to xm. So why this is snapshot, or why we are taking such a method is like, if you observe carefully here, if you compare the first points and the second points in this time series, for a given delta t, you are moving from x1 to x2. Say some term you are using and you are moving from x1 to x2. Similarly, you are moving from x2 to x3. So this kind of change for a given delta, if you are seeing, so that's how so you are transforming from x1 to x2. In the higher dimensional space, you will try to see how you are moving from x1 to x2 by using a operator called the Koopman operator k. So you will be coming to x2 after some operation carried out by k on the x matrix. You will come into the x2 point. So that's the basic theory. Now, so once you know that, so the basic equation, if you write, we will see that x prime is equal to the matrix sum operator A times the actual snapshot matrix X. Now, so this operator can change from the x1 dot or the x prime, that is x2, x3 or 2, by the operation of x on x. So if you take only the first point, if you see, x2 is equal to A times x1. And if we observe carefully, we need to perform, so if you see carefully, it seems like you need different operators for transforming from each point to the other point, because if in a nonlinear system, it's not so trivial that you will be using same matrix to go from one point to another. It can be changing in different ways. So we need to, it feels like we need to have an infinite number of matrices to convert from one point to another as we are moving from x1 to xm minus 1. So so actually we don't need to do that many number of matrices. We are actually trying to, so in a data driven approach, the main thing we try to do is try to fit a linear, so it's called the least square method, or in short, if I try to explain, okay, I will just move on to this share screen to explain it more clearly. So were you able to understand, or I am going faster, or okay. So just right here, so say we have the data which we measure. This can be any measured data, so it should be the parameter which it should be observable, that is, it represents the state of the system. So we have the data which we measure. So in a combustor, or in our cases, we try to measure the pressure of the system using a piezoelectric pressure transducers. And similarly, in brain you have a scalp, and on the scalp you have the electrodes being placed to get the EEG data and all. So Like that you have different measurements. Say you have certain number of time series xj you have, which is nothing but a value at each time step you have that. Now we consider that we are measuring directly from the system. So we mentioned that x, the capital X, is a snapshot matrix of each separate one, x1, x2, x3, it keeps on going up to xm minus 1, and so this is called one snapshot at each time step of the observable. Similarly, now after a delta t change, you are now reaching to some other point x2, x3 and all xm you reached. So we say that you are shifting from x1 to x2 by some operator a, we say. So in short we say x prime is a linear function of x. So it's like it is an operator which takes us from the current state to the future state. So that's the a operator which we are showing here. Now when you have this form, and if you try to multiply both sides with a so now multiply both sides with, so if you want to, so in matrix you might have learned that if you are having certain x transpose is equal to ax, you had to get the a matrix, you will try to multiply both sides with x and you will finally, okay sorry, this is, that example was opposite, a into x transpose if you had. So this, if you as an orthogonal vectors, you will find matrix, then you will finally see that a is equal to x into x transpose you will be getting. Similar approach only, but in these cases the problem is you will not be, every time you will not be having a square matrix. So is this cases of taking a transpose and x into x transpose, this inverse condition, so what we call a into a inverse equal to I condition is defined for a square matrix. When you are having n cross 3 cross 3 or n cross n matrix, you are having this a into a inverse can be taken as n, and you need to satisfy a lot of other conditions also. But when you are having a non square matrix, when you are having 4 cross 3 or 3 cross 4, we need to consider a other sum. So instead of saying a into a inverse is equal to I, we try to see that we will have something like a into a pseudo inverse is approximately equal to the identity matrix. So we can't say it's exactly identity matrix, but we do certain pseudo inverse, we say to this, and we do this pseudo inverse, and upon the a, if you do, you will get an approximate value of identity matrix. And remember, here it is not a square matrix, these are all non-square matrices which we are considering. So we will try to do this in a general form. So that's why we multiply both sides with the pseudo inverse, which is nothing but a dagger we say. So you had x in prime equal to ax. Now we multiply both sides with the dagger over here. So I will rewrite as ax equal to x prime, and so a will be a into x times x dagger will be equal to x prime times x dagger. So x into x dagger is approximately into unity, so you will have a approximately equal to x prime times x dagger. So what this pseudo inverse tries to do is, this x dagger is, it takes a least square regression So it does a least square regression, and so it's also called Moore-Penrose algorithm. So using this pseudo inverse Penrose, we try to calculate the pseudo inverse of the given matrix, and we finally, now you can find the operator which is converting from a given x to x prime. So it's a least square fitted one, and so I hope least square fitting and all is familiar with you. If you have a different number of points being here in a regression, you try to fit a particular line over this which can tell you the dynamics of that randomly spreaded points. And so this A is a least square fitted one, and the matrix that, so if you are saying from x1 to x2 you are going, you will have certain A value. Now when you are moving from x2 to x3, same A may not satisfy this game, same thing, but the matrix we are considering is, so the matrix we consider over the transformation from from x to x prime, right? X to x prime is the matrix where we try to fit all their all the matrices, and we choose the one that has smallest least square errors. So this is the matrix which we choose to, so this is the operator. So if you see from x1 to x2 you are having different operators, you will have a bunch of matrices, but we are in a Koopman framework, we are trying to look into a single matrix that kind of best does all of them with the smallest least square errors. So that's the idea that we try to use in the Koopman framework. So if you see this, when you are doing a pseudo inverse, say we had A is equal to x prime times x dagger you had, so you had certain number of, so if you consider this as a matrix rows and this as a matrix columns, you will, after doing this x prime into x dagger, you will be having a square matrix over here, but the square matrix will have a, now we were doing all this on the high dimensional data which we had, so this will be having some, in a fluid dynamics if you see, it will be having some billion cross billion number of points it will be having. Now solving this billion cross billion is very difficult, and we don't need to do that billion cross billion number of solving this matrix is not required for actually understanding how the system behaves and all. So instead we do is, instead we will do the lower dimensional rank reduction, or we say truncated matrix, so using which, such that we consider the fact that the low rank structure exists, and so such matrix which has this low rank reduction, after low rank reduction the matrix which we get with that, so our objective is to work with this A R cross R is our work with, rather than working with working with the n cross n, which is a billion cross billion. Instead of that, we want to focus on we will be using this rank reduced matrix in order to ease the computational efforts and all. So now said that, we will now try to move further. So as I said, x a equal to x prime into x dagger we wrote. So now this x prime is approximately equal to a times x we know. So in the case of so if you consider initially an assumption of, assume that there is a uniform sampling in time, if you are taking here, then it's normally like your maps x and k plus 1 is a times xk. So you will be able to write in this form. Now, so mathematically what we try to do is we find the best fit operator, that is a that we are trying to find. So we express it as an optimization problem using the, so I'll write it down. So we express this determination of the operator as an optimization problem using the, so what we call the Frobenius norm. So Frobenius norm is nothing but our normal Euclidean norm only, but in case of matrices we try to do that. So okay, I will just write that. So Frobenius norm we say, so it's usually represented by in this form, and we write f over here to represent the Frobenius. So it's a way to measure the size or amplitude of a matrix. So in order to understand that, if it is like it's a generalization of the Euclidean norm for vectors. So we had, if you have two vectors x2 minus x1 the whole square, square root of x2 minus x1 the whole square, how we write, same generalization of this Euclidean norm vectors to matrices is what Frobenius norm does. So in short, say for a matrix A with dimensions of m cross n, if you have, then the Frobenius norm can be defined as so the norm of a Frobenius is nothing but the square root of sigma I equal to 1 to m, j equal to 1 to n modulo each element square. So if you had a matrix a12, a11, a12 and so on, and you had a21 and so on, if you had, now this is the matrix you had. So we try to take square of each element, that's what is written here, over the total rows and over the total columns, and then we try to take the root of that. So the Frobenius norm tries to do this optimization problem, and we see at which point we are able to get this matrix A with the least error. So that's what the norm by norm we try to do there. So it's like now an optimization problem where you are getting the least error. We try to take that as an operator and we try to find the things. Now said that, so in short, if I write, our objective is to minimize the norm of the x prime which you had minus a times x. So you had x prime is equal to ax. Now we need to find the Frobenius norm of that x prime minus ax. So we are trying to optimize those conditions. So in short, if we write, this a is nothing but the minimum argument of a where x prime minus ax Frobenius norm is its minimum. So argument minimum is nothing but the minimum value of the function where the function value where it is minimum. That's what we mean by argument of minimum value. And so here if you write, so here x prime is your true or observed value, true or observed state at the next time step, whereas the ax is the predicted state at the next time step. So we try to minimize this error or size of this matrix. Now once say that, so now the capital A is what we are getting is nothing but x prime times x dagger. So the pseudo inverse minimizes the least square error between the observed and the predicted value. So that's why we use this, just write it down, the pseudo inverse minimizes the least squares error between the observed and predicted state. So pseudo inverse is able to do that optimization thing. So if you see, if you have say simple A inverse equation, if you observe, we usually write it as A inverse is nothing but adjoint of A by the determinant of A. Yeah, so when a matrix determinant, so if your determinant is 0, then it cannot be inverted. So where we say that the matrix is a singular matrix, it has no inverse. So in order to, so where in those conditions, if we can find some value that is almost close to the solution. So if your determinant is close to 0, you don't have any value for the inverse. But if you are able to find some value which is almost close to the solution, we can still make out very useful things from this. So it's like, so if we can find some value that is almost a solution, then still we can find really useful things. Yeah, so if A is a singular, then it has no inverse, then the non-singular matrix. So I will just write it down. So if A is singular, that is the Koopman matrix which we are talking about, and it has no inverse, say A inverse we don't have, then the non-singular matrix B, say there is some non-singular matrix B, the non-singular matrix B, it does not have an inverse in, and from the definition of, so from the definition of inverse, it's like B into B inverse should be equal to identity, whereas from the pseudo inverse, when you are doing it, that is say A star, when you take, it is defined as this A star into A is approximately equal to the identity matrix. So it's also called the Moray-Penrose pseudo inverse. So there are different methods to calculate the pseudo inverse. So I just briefly explained what is the pseudo inverse, and so I wanted to explain was when you are having a singular value, when you are having determinant tends to 0 or determinant is equal to, that's where you call it a singular matrix. There you don't have an inverse value, but if you are able to get a nearby value to the, so it determinant tends to 0, if you are able to get some values, then you will have some value for the A inverse, which can also give you a real usage for when you are using it in the real systems. That is performed by performing the pseudo inverse of the matrix, and we get an approximate value for the A inverse. Instead of getting directly A inverse, you get an approximate value called the pseudo inverse. Now, so you have the matrix, Koopman matrix A is equal to x times x dagger you had. So now we need to determine the pseudo inverse. So our step 1 in finding the Koopman operator is determine the pseudo inverse A dagger using singular value decomposition we try to do. So in short it is called SVD. So we do the singular value decomposition, and on the snapshot matrix X which we are discussing, so we do the singular value on the snapshot matrix X which we have. On this we try to do the pseudo inverse, and we try to get the matrix over here. So I hope pseudo SVD is, you may have some idea, but I will just briefly discuss over that. So SVD is a matrix factorization technique that decomposes a matrix into 3 constituent matrices it converts to. So it converts the matrix into 3 constituent matrices. In that, say you have a matrix M which is of the size M cross N. It divides, the SVD will divide you into 3 different matrices. One is U matrix, upper triangular matrix, then you will have a diagonal matrix sigma, and then you will have a lower triangular matrix called V. So the sizes will be, this will be a square matrix M cross M, diagonal matrix will be an M cross N matrix, and the V will be an N cross N matrix. So if you do this multiplication or the matrix multiplication of U into U conjugate or U into U transpose, if you do, you will get an identity matrix here. Similarly for V also, if you try to do this transpose of that, you will have an identity matrix. So here star by mean I want to say is inverse. If U into U inverse, if you do, you will be getting into an identity matrix. Now, so in the step 1, so in order to how to apply this, I will just discuss a simple example to see how the singular value decomposition is done to find the upper triangular, lower triangular matrices, and finally how you will be coming into the Koopman operator. That's what we are going to do now. So say you have a simple matrix A which has the form 1 2 minus 1 2 1 minus 1 you had. So the initial step will be, you need to take A into A transpose to find the upper triangular matrix U. First we try to do is A into A transpose we take. So when you do that, you have 1 2 minus 1 2 1 minus 1 you had, and you A transpose, when you do, you will be having 1 2 minus 1 over here, 2 1 minus 1 will be over here. So this, if you do the matrix multiplication, so I will do for this simple one over here. So it's like 1 into 1, so you will be multiplying my first row with the first column, plus 2 into 2 you will have, plus minus 1 into minus 1. Similarly you will be doing it for the each point and all, so I am not wasting time over here doing that. So finally you will be getting the matrix of the form 6 5 5 6 you will be getting. So we will call this as a W we are calling. Now this matrix is from the matrix value, you know, W into X eigenvalue decomposition. If you do that, Wx will be equal to lambda times X, then W minus lambda I times of X will be equal to 0. So now if you want to find the eigenvalues for this matrix W, we do is determinant of this W minus lambda I, we try to equate it to 0. So if you do that, so determinant of 6 5 5 6 minus lambda times the identity matrix, so that is 1 0 0 1. Now this should be equal to 0. So this will give you a determinant value of 6 minus lambda 5. You will have 5 over here and 6 minus lambda over here. So this will be equal to 0. And finally you can do this and you will come to this point. So if you solve this quadratic equation, you will get lambda 1 equal to 11 and lambda 2 equal to 1 you will get. Now we find the eigenvectors of the, so these are the eigenvalues of the system. Now we need to find the eigenvectors for U. So in order to do that, we know that A minus lambda or W minus lambda I into X should be equal to 0. So we are trying to find the X here. So that means you had 6 minus lambda 5 5 6 minus lambda from the equation times the x1 x2 should be equal to 0 matrix. Now we will take for a first case where lambda 1 equal to 11 if you are taking. So if you are taking that lambda equal to 11, so you will have minus 5 5 5 and minus 5 over here, and you will be having x1 comma x2 over here. This will be equal to 0. So if you equate that, you will have minus 5x1 plus 5x2 equal to 0. So if you take x1 equal to minus 1, then you will have x2 equal to minus 1. So your eigenvector here will be minus 1 comma minus 1. So that is your first eigenvector, you see. Now for the case of lambda 2 equal to 1, if you take, then you will have 5 5 all over here, and you will have x1 comma x2 which is equal to 0. Then if you expand it, you will have 5x1 plus 5x2 equal to 0. And if we take here also x1 as minus 1, then you will have x2 equal to 1. So the next eigenvector you have is minus 1 comma 1. So the net eigenvectors you have is nothing but minus 1 comma minus 1 minus 1 1. So this was your first eigenvector, this is your second eigenvector. Now in finding U, we try to we will normalize this value. So we will take the normalized U in our system. So our normalized U will be our first vector, that is minus 1 comma minus 1, and we try to do the normalization by the, if you are taking this first one, so we take that corresponding row and corresponding column values, we multiply them. So it's vector multiplication we do. So it's like minus 1 comma minus 1 times minus 1 comma minus 1 will do. So then you will finally come up to a value of minus 1 comma root 2 minus 1 comma root 2. So this is the final one value for the vector U. Similarly, if you do the same procedure for the next vector v2, you will finally come to a normalized normalized U value of minus 1 by root 2 minus 1 by root 2. Here also you will have minus 1 by root 2, and here you will have plus 1 by root 2. So this is the U matrix that you have got over here. And now, so we got U over here. okay, sorry, if I should not write A, it will be confusing with the Koopman value, so we will write it as small a. Now, so for finding U, we did A into A transpose. Now to find V matrix, we try to do is we do A transpose into A. So our A transpose, so our A matrix was 1 2 minus 1. So I will just write over here. A was 1 2 minus 1 and the other was 2 1 minus 1. So you had 2 1 minus 1 you had. Now if you take A transpose over here, thus it is 1 2 minus 1, 2 1 minus 1 you had, and A is 1 2 minus 1, 2 1 minus 1. So earlier when you did A into A transpose, your A is having a size of 2 rows and 3 columns. So it was 2 cross 3 against 3 cross 2. So your final result was a 2 cross 2 matrix. But now when you are doing A transpose into A, so you have a 3 rows comma 2 columns into 2 cross 3. So you will be coming up to a 3 cross 3 matrix. So for this current matrix A into A transpose, if you do this multiplication, you will come up with the value of 5 4 minus 3, 4 5 minus 3 and minus 3 comma 2. So this will be your A into A transpose into A, and you do, so this will be your say W dash, and you try to W dash x is equal to lambda x you will try to make, and you will do the same procedure. W dash minus lambda I matrix determinant should be equal to 0, and you will get a cubic equation now of the form minus lambda cube plus 12 lambda square minus 11 lambda equal to 0. So this will be the equation you will be boiled down to, and you will have the eigenvalues of 0, 1 and 11. So with these eigenvalues you need to find the eigenvectors for them once again. The same procedure what we did for U. So I will not be doing here. So finally you will be getting V of the form say 0.625639, sorry, and here it will be 0.707, it will be 0.3015, this will be 0.639 minus 0.707, 0.3015 minus 0.4260 and 0.904. So this is the V matrix that you have obtained. So you have obtained U, you have obtained V, and now you need to find the diagonal matrix D. So diagonal matrix of U into diagonal matrix of V if you do. So this is nothing but taking the eigenvalues over the matrix. So you will be having eigenvalues over the diagonal if you try to take for this thing, if you will have 0 and 0 0 0 you will be having. So since you are taking the single repeating eigenvalues, you don't need to consider. So you will have 0 already over here, so you have root 1 and root 11 over here. Now if you multiply them, you will get the diagonal matrix, which is nearly 3.3170010. So we are just taking the root out and decimal values we have written here. So this will be your diagonal value. So now you have converted your matrix A x prime into x dagger into a U sigma D condition, sorry, U sigma V value we have converted into. Now, so still here it is in the n cross n dimension. So it is in the higher dimension values. So it is still in the n cross n space. So step 2 to find the Koopman operator we do is we take the similarity transformation. We will see how it is done to get a low rank embedding space. So in order to get this, so what we do is we have A, which is nothing but x prime times x dagger, and you had the x which you just wrote it as u is nothing but ud, and we take the v times v transpose we take here. So this is the definition of x in the you are doing the singular value decomposition. And if you take x dagger, so it is nearly like an inverse you are doing, so you will get u transpose d inverse v. So you will be boiling down to this, and so here a will be n cross n. So since x and x dagger you are substituting back here, you will have x dagger and x trans here. So I will just put the dagger values here. So it's like u transpose d inverse v you have. So this is your matrix, Koopman matrix A in n cross n. Now we compute the projection of A onto those leading singular vectors, which results in a smaller vector A tilde, which is of the size r cross r. So here is where we do the dimensionality reduction. So we compute the projection of A onto these leading singular vectors, and which results in a small matrix A tilde, which is of the size of the rank of the r cross r. Not right, the lower dimensional reduction, how much is the r value, that reduced r cross r square matrix you will be boiling down to. So the columns of the matrix U are also known as the proper orthogonal decomposition modes, and they satisfy this normal condition. So I will write it down. So and one more property is the columns of the matrix U. Oh, sorry. Oh, it went off. Okay. So the columns of the matrix U are also known as the proper orthogonal, once again is the recording good, are also known as the proper orthogonal decomposition, or we call the POD modes, which and they satisfy, we have mentioned already that they satisfy the condition u transpose into u is equal to I. Now similarly the columns of V also will satisfy this, when V also will satisfy these conditions. Now we are only interested in the leading R eigenvalues and eigenvectors of A. So we are interested in the leading R eigenvalues and eigenvectors of A, and we may thus project the A matrix onto the decomposed, properly or not decomposed modes in U. So when we do that, so say you had, when you are doing that projection over to U, so you had A R cross R. Now when you are doing the projection, it will become U A transpose into U, U transpose A into U, and since we know that our A higher dimensional n cross n Koopman operator, it is, we derived it above, it's not there, we will just write it, it's like x prime v d inverse u transpose you had. Now when you are doing this projection onto this, when you are doing this projection onto the modes in the U, that is proper orthogonal decomposition modes, we are projecting the A onto this POD modes in the U. So you will get into A R cross R. So we just put tilde over here when changing. So you will be coming down to U transpose X prime V D inverse. So how we got this is, you are anyway projecting this onto this U. So okay, I will just trim this and write a little down. I will write 2 more lines for that. So what we do is, so we had A n cross n is equal to X prime V D inverse U transpose. So your A R cross R is nothing but U transpose AU, and you substitute the A into this. So U transpose into X prime V D inverse into U transpose times U. So if you observe here, U transpose into U is identity. So you will boil down to U transpose X prime V D inverse. So this is the lower dimensional Koopman operator value where we need to work on. And so this is not, this is what we have written up here. Yeah, so the last, when, so this is the A tilde. This A tilde has the same non-zero eigenvalues as the full matrix A. So our eigenvalues have not changed over here. So thus we need only compute, we need to only compute the reduced A tilde directly instead of solving the higher billion cross billion matrix. So in a turbulence, if you see this billion cross billion, when you are doing the dimensionality reduction from a billion cross billion, we are actually reducing it to some 200 cross 200 matrix we are boiling down to. So this kind of reduction we are able to get in this thing. Yeah. So directly without ever working with the higher dimensional A matrix. So that's the key advantage over here. For by we are doing the singular value decomposition and getting to a lower dimensional reduced model. And this reduced order matrix A tilde, it defines a linear model for the dynamics of the vector POD. Okay, that also I will write, that's also important. So the reduced order matrix A tilde, it defines a linear model for the dynamics of the vector of POD coefficients of X. So it's, say if you have, say some X double prime, you had the POD coefficient, then X double prime n plus 1 is approximately equal to A times the previous xk. So this how you can write into, when you are doing the periodic coefficients, you can take and you can directly write the linearized model over here. So once we have got the singular value decomposition and you have done the similarity transformation for rank reduction, the next step is finding the eigenvalue decomposition. So this we can directly do is, we have the A r cross r vector and A times W will be equal to W times the lambda. So here W is this and this W's are same. So this W's refers to the eigenvectors. So the entries of the diagonal matrix of eigenvalues are the DMD eigenvalues. Sorry, so I will write here the columns of W are the eigenvectors of A tilde and provide a coordinate transformation that diagonalizes the matrix. So it diagonalizes this matrix A R cross R thing, whereas this gamma which is shown here, these are the eigen values. So these entries of the diagonal matrix, so it will be a diagonal matrix, are the diagonal matrix of this capital gamma are the DMD eigenvalues. So it's the decomposed eigenvalues which also correspond to eigenvalues of the full matrix A, full capital A matrix. So we try to do the eigenvalue decomposition. So we don't need to do all the things on the complete A n cross n. Now we are doing to, and this shows a similar eigenvalues, dominant eigenvalues of the capital A, which is of n cross n matrix. Now the step 4 is, now you did all this, now we need to bring this back to the original space. So we had the high dimensional dynamic mode decomposed modes, say we represent it by 5, are constructed. They are constructed using the eigenvectors of these are W of the reduced system, and now we need to find for the next time shifted snapshot. Okay, sorry, this is the time shifted snapshot, that is xn plus 1 matrix of x according to get back to the high dimensional space. So we did everything in the Koopman space, then we came back by doing the constructing the eigenvectors W of the reduced system and doing the time shifted snapshot over this, we will be getting back to the high dimensional space. So how we do this? So we did said that the high dimensional DMD modes 5 are there. This can be shown by x prime d inverse times the eigenvector. Now for this we have a I am not writing the intermediate steps. Now we have a solution which is of the form x is equal to your total DMD modes times e to the power omega t times b. So this b is a constant and it changes with the values, so it's not much important here, but here we can see is you will get for different modes from k equal to r to 1 to r, this you can find for the different values of frequencies if you are having here, and this bk. So you can use from one how many modes you want to be converting into, and what are the dominant modes from 1 to r you can take, and you can take the summation of it to get back to this. So if you see, so how they prove that you are actually getting back to the so you now need, you got something, you did step 1, step 2, step 3 for finding the eigenvalues, you did a rank reduction to get a lower Koopman operator, and then on that you did the analysis and you got some solution, and here we are showing that it's an exponential term sitting over here and it should be increasing. Now how these DMD modes are eigenvectors of the high dimensional A matrix is, how are they true? It needs to be proved actually. So for that what we do is, these DMD, whatever answer you got, is it corresponding to the actual high dimensional space or not, we need to prove. So for that, a simple equation what it was, how it was proved was, so it states that these DMD modes are eigenvalues of the high dimensional matrix A matrix A corresponding to the eigenvalues of lambda. So that means if you are able to show like a phi is equal to phi of lambda, then it proves that the eigenvalues and eigenvectors which you have found is actually corresponding to the high dimensional space over there. So the say now you consider some other function phi. This is okay, this is nothing but our phi which I have shown here, that is x prime v d inverse of w which you have here. And if you take a times of this phi, so a we know it is nothing but x prime v d inverse of u or u transpose if you take, and this x prime v d inverse w. So if you observe here, this u transpose x d inverse is nothing but the a tilde, that is the reduced order thing. So you will be left out with x d inverse a tilde times w. So x, so a phi this was. Now when you are having eigenvector, we wrote that a omega aw is nothing but w times the eigenvalue. That means a times y will be equal to x prime v d inverse a tilde omega is nothing but w times the eigenvalues. So a5 is nothing but, this is nothing but our phi times omega. So this proves that a phi is equal to phi omega. So actually you are actually finding the eigenvalues of the actual Koopman actual high dimensional space itself you were able to do, and the solution which we found like x is equal to phi times e to the power omega tb, this actually gives back to you the actual values which you are finding from the Koopman operator space. So this shift is correct, and it was proved by this simple way of saying that a phi is equal to phi I omega we say, and this equality which was able to show, and people were able to convince that actually when you are doing it in the Koopman operator space and when you are projecting it back to the high dimensional space, you are actually getting the dominant modes that are present in the system. And so I will just go back to the PPT over here. So in short, we started with the snapshot matrix, then we did the pseudo inverse to find the value of Koopman operator, which moves from ax to xk plus 1 it wanted to move. So actually we did was an optimization problem where we had the least square errors to be as minimum as possible. That is the operator which we considered for as a Koopman operator. And we did the A inverse thing where we said that why we need to do a pseudo inverse, and our first step was to do a singular value decomposition, and we did the decomposition for a simple example we tried to do, and we found the u, v and diagonal matrix for that system. Then we did a low rank embedding space by reducing the actual matrix into an R cross R matrix, which is by projecting the actual A n cross n onto a p proper orthogonal decomposition modes in the u value on the u that we have determined. So, and finally you will be coming into an R cross R matrix where you can say that the reduced order A tilde which defines a linear model for the dynamics of the vector, and then you did the eigenvalue decomposition to find the eigenvalues of the matrix A R cross R. Now this is a low dimensional matrix and you are able to get the values of each of them sorry, so these are in the opposite, the written things are opposite. So this should be of the columns of omega and this should be diagonal matrix. And then we looked into the how to bring this back, the high dimensional DMD modes which we constructed, how we need to bring it back to the high dimensional space. So we saw how these exponential terms come into, and we proved that this actually they are finding the high dimensional space, they are able to bring them back from the Koopman space, and we had the solution of that finally. Now I will just show you how a I'm presenting it. Okay, so I will just so this is a simple EDMD code where we can just try out. So here we are not, so if you see there are very more standard ways of doing the EDMD. So not EDMD, we say in dynamic mode decomposition there is something called as extended dynamic mode decomposition, and there are a lot more further processes have been carried out in the DMD modes and finding the Koopman operator space. So there people try to do different things over there. So here I'll be just showing you a simple code where we will find a simple Koopman operator and we will try to predict the actual time series. Now there are advanced techniques called extended dynamic mode decomposition and all these things, where they try to update the Koopman operator as it progresses. So this gives you more accurate results when compared to the simple dynamic mode decomposition based Koopman operator application. And people have done a lot of work on this EDMD methods. And so now I will show you, here I am showing you a simple dynamic system. So say you take a, we will run this code in the MATLAB within few minutes. So simple, we have a dynamic system of, so I just divided the time into a line space between from 0 to 10,000. I divided as in steps of 50, and here I consider a sine wave for simulated as the state variable. You can replace with any of the data we have, and I take a window size of 100. Then the number of snapshots which I take for measuring this is the total length of this sine wave, that is 10,000, minus the window size which I have mentioned, plus 1 which I do. So you will be getting from 1 to 100, then the next snapshot. So that, like that you will be having these many number of snapshots being present over here. And initially I initialize all the values in the matrix of x to zeros. So here window size comma the number of snapshots will give you a matrix where you will have a matrix with all zeros initially. Then I run a for loop from 1 to the number of snapshots, whereas where we progress from each x, y. So if I is equal to 1, so it will be like you will have all the rows and the first column you will be taking up to. So from ix, so the first column will be filled up with 1 to the 1 plus window size minus 1. So this will be up to 1 to window size. So 1 to 100 points will be stored up in the first column of the matrix. That is the first snapshot. Now in the next snapshot, when it moves from 2 to 100 plus 1, so it will be moving from 2 to 100 not 1. So like that you will be progressing up to the total number of snapshots which I have mentioned, which we calculate from here. And that is now our snapshot matrix which we have. That was our x which we have in our system. Now we perform the singular value decomposition over it. So matrix, MATLAB has a simple code SVD. If you type, you can give the matrix over here and you can do the singular value decomposition. So economic is a simple way of doing this singular value decomposition over here. So you will get U, S and V matrices over here. So for convenience I just kept two modes to be dominant, considered two mode, the k equal to 1 to r we can consider. So I have considered two modes. So now once we come fix that, so with the matrix U, R, that is the reduced order matrix, when the U is projected onto this R, you will have U ranging from 1 to R. So 2 is the number of modes we have selected. So 1 to 2 it will go to. So the first two columns of this U vector and the first R column rows and first R columns of the first r columns of this S is nothing but our diagonal matrix we will be taking, and V will be the lower triangular matrix. That also will take from 1 to the n minus 1 number of rows you will be considering, and 1 to r number of columns you will be taking. So these many number of modes when you are considering, that many number of columns and all it will be taking based on the SVD you have performed. So once you have calculated the Koopman operator, now we will be making the A tilde, that is the reduced order Koopman operator we need to consider. So for that, as we have written, x prime is nothing but the x value that you have taken from all the rows you need to consider with number of modes 2 to the end you will consider, and A tilde, that is our reduced order matrix, is nothing but our reduced order upper triangular matrix into the x prime, that is the actual snapshot matrix, into VR by SR. SR is nothing but the diagonal matrix. It is, you take the inverse of it actually, so that's why we wrote it down here, and into the lower triangular matrix. So that is the V, which is A tilde, which I have shown here. So I am just explaining what are the basic terms and lines here. You can run over these codes, and we can, if any questions, you can please ask me after the class. And so the number of predictions we are trying to do here is for 10,000 points we have done, and we initialize the initial condition as a matrix, say 0.2 up to 0 we take. Now using the Koopman operator space, so initially we take the predicted value, we initialize every matrix elements as zeros initially, then we store this predicted state, we run this x predicted, so that is this x predicted condition, and we try to get different values. So as you know, Koopman operator A tilde times the x will give you the predicted value, and each predicted value is stored in each of these columns shown here. So x1, you can change it to the required values. So once we have done this, we will try to run this on the MATLAB over here. Okay, just so as you can see, so so I'll just clear this off. So if we run this first, so here I have taken for cos function here. So if you run this first, evaluate over here, you will be getting the number of times steps you can see over here, the variable count up to 10,000 points it has come, and the x matrix, snapshot matrix, it has created for 500 cross 9501. So that is the matrix with n number of snapshots created for a given window size, and upon that the SVD is performed, and you will be getting the different UR, SR and VR values, that is the reduced order matrix you will be coming down to, and we are calculating the A tilde, that is our Koopman operator matrix which we are calculating. So A tilde values you will be having somewhat like this, and for a number of prediction I am considering for 10,000 prediction if I consider, and I initialize that and initialize with the initial condition. Now once done that, I will now try to predict for this given values. So if we evaluate that, so now the prediction A tilde A into x values have been calculated. So if I now try to plot the values, so this is like, okay, so this, just plot it once more. Yeah, so this red corresponds to the actual cosine wave that we have given to the system, and the predicted value by the Koopman operator matrix which we have done. You can see that there is a match between, but there is not much. As you progress in the time, you are not able to get good data matching with this. So it can do for a short term prediction, that's what we were mentioning, but if you do more EDMD methods and all, you can make it more refined, and it will be able to capture this whole dynamics. So that's why dynamic mode decomposition. Then after that, Koopman based EDMD methods are used to get more better results. So this is one of the small code which it does not explain any much of the things, but a small code to introduce to the concepts. And so this is the result of that which I have shown here. So in summary, the Koopman operator is a linear operator that operates on a functions of a dynamical system state variables, which we say as observables. It describes the evolution of these functions over time, and without directly considering the system's underlying equations, which nonlinear dynamics, which we have studied till now, was trying to use that. And using dynamical system equations, you need certain idea over the dynamics that is happening inside the system. You need to have a brief overview of what is happening inside the system. Then only you will be able to properly evaluate those equations and all. But here, when if you are having a direct data and you are not having that much understanding of the system also, still your data can able to do certain prediction values. And the operator that provides a way to analyze the system's behavior and make predictions by transforming the original nonlinear dynamics into a linear framework. So that's an additional advantage with the current status of where you are having tons of data from simulation and experiments. This method is quite helpful and people are working rigorously on that. So that's what I have prepared for. Yeah, so you were aware of this? Yeah, so, yes. So I thought when we were told that we will be teaching the data science students, I thought at the end I should be introducing some to the data driven also. Yeah, so dynamic system has limitations. So finally, without the dynamic equation also, you can use with this data, and that's how we concluded the series on X. Oh, okay, okay, okay. Oh, okay, okay. Okay, okay. Oh, okay. Oh, okay, okay, okay. Oh, okay. Two. Oh, ah, different. Oh, yes, yes, yes. Yeah, yeah, yeah. Yes, all right. Yeah, so yeah, so yeah, thank you. You at least you people were joining and you were cooperating, very patient about listening to, yeah, to us. Maybe they know. Oh, this is same link where Shruti was updating. I will send you back once again. It's the same Excel sheet. I will share you once again. So I was updating on regularly on that every day. After every session it was, yeah, that was my little younger photo. Yeah. Huh. So I think nonlinear dynamics, some people may already know it. That's why mostly did not join. Yeah. Yeah. Okay. Somewhere you will use it. Yes, sure. That's true. Yeah. Yeah. Thank you very much. I think you are very patient with me. I have 2 hours. Yeah. Okay. Oh. Okay. Okay. So here I think if they're over now, they are getting Christmas vacation. It is for IIT. So I also wanted to finish before 25th so that if Malavika they are all busy with vacation. Okay, 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 okay. Yeah. Thank you, Joe. Yeah. Yes, yes. That I will mail him. I will send the link with all the Excel videos, recordings, and all. Yeah. Okay. Thank you. Thank you. Bye. Okay.